Oh, to start with, we're talking about rationals. A rational number is a number that can be written as a fraction. That's something you should know. If you don't know it, write it down. Rational means something you can write as a fraction. All right. And the typical problem looks like this, and there's a lot of factoring involved. So like, for instance, in this one, I would... So we're going to factor the bottom part of this. Do you remember how to factor something like this? You put an x, and then what? What goes into 21, or what times what makes 21? It's probably 7 and 3, and then we want them to multiply to this, and we want them to add to that. How do we get 7 and 3 to add to 4? A positive 7 and a negative 3. Positive 7, negative 3. And now, do you remember what happens when these guys cancel? It creates something. It creates a hole. And a hole is at what? Negative 7. All right, so here's the process we usually did. We did domain, which is what numbers can go into this thing and make it work. Well, all real numbers will work, except x cannot be negative 7 and x cannot be 3. Okay. Now, there's another way to write that if you want to. You can say that it goes from negative infinity up until you hit, what's the first number you'd hit if you're going along the number line? Negative 7. And it never touches this, and it can't ever touch that either, right? And then it goes from negative 7 all the way up to 3, and it shouldn't touch either one of those. And then from 3 to infinity covers all the rest of them. So that's just two different ways you could see it written on the test for the domain. All right, next thing is vertical asymptotes. That comes from this. The asymptotes and the holes come from these guys. Each of these things is either an asymptote or it's a hole. It can't be both. All right, so which one is a hole? Negative 7. And if the hole is at x is equal to negative 7, then the other one, that 3, must be something. So what is it? That must be the vertical asymptote. For horizontal asymptotes, you remember these? Bob, bot, sob. Bigger on bottom, bigger on top, same on both. Okay, look at what we've got here. After this stuff canceled, is it bigger on bottom, bigger on top, or same on both? It's bigger on the bottom. Okay, let's go over what they mean. Bigger on bottom, bigger on top, same on both. Bigger on the bottom, we said Bob's a big fat 0. And then remember, though, that if there was anything outside the function, like y equals 1 over x plus 2, and then we had minus 3, we'd have to add in whatever was out here. Okay, so it's 0 plus, I'd like to say. It's y equals 0 plus whatever's out there. Okay, bigger on top, there's no bots. So if your thing is bigger on top, there will be no asymptote for it. And these are horizontal asymptotes we're talking about, by the way. And same on both is the ratio. There's the ones that'll make you sob because they're so hard. And it's really not that bad, though. It's a ratio of the lead coefficients. Okay, let's look back at this. What's the lead coefficient here? What's the lead coefficient here? So it'd just be 1 over 1, which would have been 1 in this case. But in this case, it wasn't the kind that makes you sob. It wasn't the SOB. This one was a bigger on the bottom. So if we would have done our y equals 0, 0 plus whatever's on the outside. There's nothing out here on the outside. So it's just y equals 0. All right, any repeats on those needed? All right, moving on. So if you saw this one, try it all by yourself. I'm going to pause while you see if you can do it. All right, so after I got it factored and nothing cancels, then I can write the domains, all real numbers, except what can't the domain be? It can't be 4, and it can't be negative 4. Then those have to either be asymptotes or holes, but they can't be both. So since they aren't holes, then they must be, both of them must be asymptotes. X equals 4 and x equals negative 4. Can you have two asymptotes? Yes, you can. And there's no holes. And is this bigger on bottom, bigger on top, or same on both? It's bigger on bottom, and Bob is a big fat 0. But plus anything out here, but there's nothing out there, so y equals 0. That the domain has nothing to do with the top. The domain is only about the bottom. Because the top, we don't care if that gets to be 0, but if the bottom is 0, you end up with a 0 in the denominator, which makes the whole Earth implode. Anything else? Okay. Okay, so on these, we're just talking graphs. My first thought would be that I know that some of these have holes and some of them don't, and I can see that this one's got a hole in it, and so does that one. So the ones that have holes, which should it be, A, B, C, or D? C would have a hole. What else would have a hole? D, all right. So this one's kind of nice because when the hole cancels completely, then what does it leave behind? A 1. And so y equals 1. So which of those two graphs looks like the graph of y equals 1? The second one, this one. So this one goes with this one. And it has a hole at 2. Does that make sense? Yeah. This other one has a hole at 2 also. And when this cancels, this one is squared, which means 2 of them. And so then I cancel one of them, and I'd have y equals x minus 2, and that is what this line is. And it's got a hole at 2, which works perfect. So that goes there. All right, then we're left with A and B must be either this one or this one. And this one's kind of your normal rational, except it's been shifted. Which way? Right 2. So that is, here's your normal rational function. In case you don't remember what they look like, they always kind of look like that to start with. They go through the key points like that. And then this one's a normal one. It's been shifted over a couple. So this one right here would go here. And that leaves by process of elimination this one, but I can do better than that. There is an asymptote running right up there at 2. Does it make sense that there'd be an asymptote at 2 for this one? Yeah, it does. All right. So, there's also an asymptote at 2 on this one, but then that made sense for that. All right, so that's graphing. Next thing is matrices. Matrices are basically collections of numbers in a rectangle. And this isn't too bad if you know some of the simple ones. You'll get some easy points by being able to add or subtract them. If I was going to subtract these two matrices, the matrices have to be the same size, like 2 by 2s, which they are. If they're the same size, you can add or subtract them. And then these two elements go together, so I just subtract those. And my answer is going to also be a 2 by 2 matrix. All makes sense. Here's my 4 spots I need. Answers in. And those two, when I subtract them, makes 0.6. And then I'd subtract these two and put the answer here, etc. That's all there is to the subtracting and adding kind. Okay? This is called scalar multiplication. This is my scale factor, and it gets multiplied by all the things that are in here. So basically, you just multiply all of those out. Now, if I wanted to find this one, for instance, I would take this times this, and it would give me that one. So 5 times 1.9, whatever that is, it's about 5 times 2, which is about 10, a little bit less, and it'll be positive because there's 2 negatives. Like 9 point something. All right, 9.5, I think. All right, moving on. This is the harder kind. They're multiplying where the matrices aren't the same size. All right, so I know that this is one of those moments where you're going to look at this and go, I don't remember how to do this. So some of you might remember, but here is a quick reminder. Say this is the question on the final. The first thing I would do is write out what this is in rows by columns. How many rows does this thing have? 3. How many columns does it have? So it's really easy because you can't even screw up the rows and columns on that one. On this one, you could. How many rows does it have? 3 rows, because rows go this way. And how many columns does it have? 3 by 1. Do you remember this? If these match, then it's going to work. And if it's going to work, this is what size matrix you'll have for an answer, a 3 by 1. Okay? So I'm going to go make a 3 by 1, 3 rows, and 1 column. So it's going to be like this. Then, you may remember, I asked you to make a map. The map here would be like this. Where exactly is this spot? What? Row 1, column 1. Is this coming back? You remember this now? And this would be row what? 2, column 1. And this would be row 3, column 1. And then, on the next video, I'll show you how to actually multiply them.